Hi everyone and welcome to day 6.5. There's no new homework assignment for this day. You should still be working on the day 6 assignment that will be due the next class period on day 7. This is in your white notes packet. See if you can flip through and find where it says 3-6.5. And today is essentially going to be a discovery day. We're going to discover some stuff about exponential functions and their slopes. So what we're going to do is we're going to pause the video for 2 minutes and see if you can do part A. Feel free to work with someone nearby you if you are unsure, and we will need our calculators a lot in this activity today, so make sure to have those out as well. So again, we'll pause for 2 minutes and let you work on part A. So in part A, hopefully we did something like 5,000 times 1.10 or 1.1, because when you want to increase by a percent, you want to keep what's already there and then go up an additional 10%. So think of it as 100% plus 10% is 110%, and then switch that to a decimal. So we should have gotten $5,500 for 1 year. And then after 10 years, we would want to do something like 1.10 raised to the 10th. Now, normally in AP, we round to 3 places, but we're dealing with money in this case. So we've got to the nearest cent. Well, notice we have repeated multiplication. Take a moment and turn to someone nearby and share what type of function would best represent this scenario. I heard a couple people off to the left side say an exponential function. That's exactly right. So if we wanted to write a function to represent this, we could do something like y equals 5,000 times 1.10 to the x, where x is representing our time in years and y is representing the value of the portfolio. And I guess I never wrote it down here, but we had exponential for the first part. In part C, let's just sketch what the graph would roughly look like. It's exponential and it's growth. So some things we know are the y-intercept should be 5,000. And then it should look something like that. So going across the y-axis at 5,000 and then exponential growth. Now for D, what is the rate of growth at those specific x values? Well, rate, we want to think slope. If it's at a single point, we want to think slope of a tangent line. Well, right now, we don't know how to do the derivative of exponential functions. Hopefully by the end of this video, you will be able to. But right now, we don't. So the options we have. One, we could do some slopes of secant lines and pick, say, like 5 and 5.01 and do the slope between those 2 points, and that would give us a pretty good approximation. Another thing we can do is we can use our calculator to help us out. So if we go over to a graphs page and graph our exponential function that we have, we'll want to change our window. We're at 5,000 for the y-intercept, so I'm going to do like 8,000. And let's see, actually we want to see 5 and 10 And we know from 10 that it was 12,000, so I should actually probably change this to something higher. Let's do like 15,000. Now, since we want to find the slope at 10 as well, I'm going to make this x value a little higher. Let's make that 15. So now we got a good view of the graph from 0 to 10, so we can see the two values we want, x equals 5 and x equals 10. When you're on a graph, the most common thing that you use is menu analyze graph. So we'll go menu analyze graph, and we can go to dy dx. It asks us the position. Well, the first one we want is 5. So just type in 5, and it tells us what that derivative is. So we've got 767.49. So we can say at x equals 5, dy dx equals 767.49. And it's a rate, so our unit should be something per something. It should be the y units per the x units. So in this case, we have dollars per year. Take a moment, see if you can do the same idea to find at x equals 10. And we should get $1,236.05 per year. So that's just a tool we have on our graphs page of the calculator to actually find what our derivative is at a given value of x. So if we move over to the next page, so we've got two different exponential functions here. We have some basic ones, y equals 2 to the x and y equals 3 to the x. And what we're going to do is we're going to start examining the derivatives a little bit about these. Well, derivative is slope of the tangent line. So let's think about some of the different things we notice about the slopes. So we're going to pause the video for 1 minute and just have a discussion with someone nearby about what are some things you notice about the slopes in these two graphs. So hopefully you had a good discussion there. The things that tend to come up in years past is one, you have the slopes are always positive. And another thing that always tends to come up is the slopes are increasing. You may have had some other things as well, but those are two common ones that tend to come up. So what we're going to do is we're going to basically start to plot what the derivative function would look like. And what we're going to do is for each of these, we're going to find what the derivative is at, we'll do 0, 1, and 2. So for y equals 2 to the x, we want 0, 1, and 2. And we want to know what dy dx is. And then once you get those values, you're going to plot them on the new graph, or on the same graph as 2 to the x. Okay, so you'll have the derivative right on there. And then at the same time, you're going to do it for 3 to the x. We'll do it at x equals 0, 1, and 2. Figure out what dy dx is, and plot those as points on the 3 to the x graph as well. So this will take a few minutes, so we're gonna pause the video for maybe 4 minutes for you to go ahead and do that. So we have here the graphs that you should hopefully have. You can see in the t-tables the derivative values you got, and then those are plotted in the red there. So we're going to pause for 1 minute, and see if you can write down some observations that you notice of your derivative graphs there. So the thing that usually comes up is that in 2 to the x, the derivative graph is below. So in 2 to the x, dy dx is below, while in 3 to the x, dy dx is above. If we flip over to the next page, so part D talks about that. You may notice derivative of 2 to the x is below the original graph of 2 to the x. The derivative graph of 3 to the x is above the derivative graph, or the regular graph of 3 to the x. So we want to think about, is there an exponential function whose graph is exactly the same as the original? So again, 2 to the x was a little bit below, and 3 to the x is a little bit above. So is there something in the form y equals a to the x? What value of a would maybe be exactly on the original graph? See if you can share with someone nearby if you might have any ideas. If you're unsure, think what's a number that we use frequently in math that falls in between 2 and 3? Well, one that does fall in between is e to the x. So that would maybe be one that you would think. Well, if e is going to be exactly on, so some conjectures we could make, and we'll test them out. If we're in the form y equals a times b to the x, let's say. Actually, no, let's just call it a to the x because we had a basic form. If we have y equals a to the x, we're saying above that if a is equal to e, the graphs are the same. But what we noticed for 2 is it was below. So maybe that means if a is less than e, dy dx is below. And if a is greater than e, so like 3 to the x, dy dx is above. And maybe we'll add dy dx is below y, and dy dx is above y, just so we're clear in relation to. So what I would like you to do, so we've got 3 equations we're working with. Y equals e to the x, y equals 2 to the x, and y equals 3 to the x. We want to see if we can prove that e to the x's derivative is in fact the same graph. Can we prove 2 to the x's derivative is in fact below the graph of 2 to the x? And can we prove 3 to the x's derivative is actually above the graph of 3 to the x? So what we're going to do is we're going to pause for a bit here. So we're going to pause for maybe, let's pause for like 8 minutes, we'll say. See if you can algebraically prove those 3 things that we just mentioned. Okay, use techniques that we've done so far and see if you can figure out a way to prove that e to the x's derivative is the same graph, 2 to the x's derivative is below, and 3 to the x's is above. So we'll give you 8 minutes to do that now. There's some different ways that we could do this. One of them is using logarithmic differentiation, which we saw the other day. So if we did natural log of y is equal to natural log of e to the x, this becomes natural log of y equals x natural log of e. Well, natural log of e is just 1. So this is really just natural log of y equals x. So we can do implicit differentiation now. Derivative of natural log of y would be 1 over y times dy over dx, because we're doing a derivative of y, and derivative of x is just 1. Well, if we multiply the dy dx over, we just get dy dx is y, replace y with what it was equal to, and we get that it's e to the x. So we just proved there that e to the x's derivative is in fact itself. Well, let's try 2 to the x, see if we can do the same thing. So we'd have natural log of y equals natural log of 2 to the x. That's natural log of y equals x natural log of 2. So keep in mind, natural log of 2 is just a number. So when we go to do our derivative now, natural log of y's derivative is 1 over y dy dx again. If we had 7x, the derivative would be 7. So if we have natural log of 2 times x, the derivative is just natural log of 2. We'll multiply the y over, and we'll have natural log of 2 times y. We can replace y with what it was equal to, so we'll have natural log of 2 times 2 to the x. Well, the value of natural log of 2 is about 0.69 or so. That is less than 1, so when you multiply it by the original graph 2 to the x, it's always going to be a little bit below. So that proves that 2 to the x's derivative is a little bit below the graph. And lastly, we'll do the same thing for 3 to the x. So we'll have ln y equals natural log of 3 to the x. That's natural log of y equals x natural log of 3. We'll do 1 over y times dy dx equals natural log of 3. dy dx is just natural log of 3 times y. And in the end, we'll get dy dx is equal to natural log of 3 times 3 to the x. Well, natural log of 3's value is around 1.10 or so, if you round it to 2 places. When you multiply by that, it's a little bit bigger than the original graph. So we, in fact, did just prove that. Well, let's see. 2 to the x's derivative was 2 to the x times natural log 2. 3 to the x was 3 to the x natural log of 3. Why is e to the x just e to the x? Well, if we followed the pattern of the others, that would be like having a natural log of e here. Remember, we simplified that natural log of e to be just 1 before, and so that's really there, but the natural log of e is just 1, so it doesn't end up appearing. So off to the side, or wherever you have room, you can put it above. Let's just write our general rule. If you have y equals a to the x, dy dx should equal, and take 20 seconds to see if you could write what the derivative should be. And hopefully you get natural log of a times a to the x. So that's what we'll always have when we have a base raised to x for an exponential function. So to finish this out, let's go back to that original one that we looked at. So we had y equals 5,000 times 1.10 to the x. Well, this is just out front. Just like if you had a 5,000 in front of a sign, you would just leave the 5,000 out front and do sign's derivative. So when we do our derivative here, we'll just leave the 5,000 out front, and now do the derivative of 1.10 to the x. Well, that should be natural log of 1.10 times 1.10 to the x. And what I want you to do to finish this out, check that at x equals 5 and x equals 10. We're working with money here, so we'll go to 2 decimal places and just compare and see if that is in fact the same. So we'll pause the video for 1 minute for you to do that. So we should have noted that it was the same. We should have got 767.49. Remember, our units is dollars per year. And $1,236 or $1,236.05 per year. So hopefully after this video, you are now comfortable with our derivative of any exponential of the form a to the x. You've got your day 6 homework that is due tomorrow. Have a great rest of your day.